Hi there, I found this old power supply on eBay for less than £10 and I was attracted by the strange user interface with these buttons. It also does a symmetric plus-minus voltage, which none of my other power supplies does. So I thought maybe I can fix it, and worst case, I might still get some useful parts, heat sinks and enclosure. Clearly the two black buttons on the top are for the meter. With two buttons you get 4 possible combinations depending if they are out, which is shown as a large square, or pushed in as a smaller square. They are using this to select between 30 volts and 10 volts or 6 amps and 2 amps. The other buttons select 4 different ranges: 0 to 30 volts, 1 amp, 0 to 15 volts, 2 amps, 0 to 7.5 volts, 4 amps, and finally 5 volts, 4 amps. Strangely, you can push more than one of these in, which I did not expect. I would have expected pushing one in would release any other. On the back is the large heatsink with 4 power transistors of the good old 2N3055 type. On the left is a mains voltage selector looking more like sort of a plug. Opening is very easy since the unit came with all screws missing already. Between the front and rear panel are 2 vertical PCBs. A large one on one side and a smaller one opposite. A large transformer sits in between and the whole thing is very filthy. Here's a view from the other side, clearly showing the PCB that has the push buttons on it. Of note, this unit uses only discrete transistors, not a single IC inside. A better view of the transformer, and there is actually a third PCB at the bottom of the front panel where the output sockets are. Slightly hesitant, I decided to power it up. It doesn't explode and actually shows some voltage on the meter. And the buttons do something, but I'm not sure what. I need to read the manual that I downloaded. I think I got it now. Only the 30 volt button is on and the meter is also selected to show 30 volts. I can change the voltage between 15.7 and way more than 30 volts, which I did not do because of the analog meter. I should be able to select between 0 and 30 volts, but at least it kind of still works. Let's test the symmetric output. 15.7 between the outer terminals, but using the center terminal I get the expected 7.8 on one side and the same on the other side, so that seems to work just fine. The 15 volts range now, and like before, its lowest value is 11.1 instead of 0, and it goes beyond 15 volts on the high side. And the 0 to 7.5 volt range goes between 15 volts and 7.5 volts instead. Well, at least the fixed 5 volt range is clearly spot on. And if I change the meter to the 10 volt range, it shows the 5 volts smack in the middle. I thought it might be useful to have a quick look at the schematics. There are versions of this power supply with different voltage ranges and without center tap. Also, there is a later version that uses op amps, so it's important to find the right schematic. I also found an addendum sheet which changes, and after stumbling over a resistor called R45 on the main board, I realized it applied to my unit. The addendum sheet only lists the changes but did not update the drawings, hence I actually corrected the schematic with these highlighted changes using a drawing program. First impression is that this is quite an elaborate power supply, and this is only the part without the splitter for the symmetric voltages, which adds another 10 transistors into the mix. There is a rather confusing number of switches, which are the push buttons, but it's relatively simple. When selecting between ranges 30 volts, 15 volts, 7.5 volts, the push buttons have 3 sets of contacts that do things simultaneously. One set switches the transformer taps, so the 15 volts gets less AC input but higher current, and 7.5 volts gets even lower AC volts but yet more current. The second set of switches changes the set voltage range of the stabilizing circuit, and the third set changes the setting of the current limiter. Since this is a linear power supply, the power transistors have to convert any unwanted voltage at the output into heat. If you selected 5 volts in a 30 volt range at 4 amps, this would be 25 volts times 4 amps or 100 watts, which is more than they can handle, especially without fans. Hence, the 30 volts is limited to 1 amp for a maximum 30 watt heat production. Actually a little more, because the input voltage has to be of course a little higher to get 30 volts out. For 15 volts, the current limiter can be changed to 2 amps because the transformer tap change reduces the input voltage, and the same happens again for 7.5 volts. Measuring the voltage at the big smoothing cap shows the selection of the transformer taps in action. In the 30 volt range, the power transistors are actually getting nearly 43 volts input. Selecting 15 volts drops the main voltage to nearly 32 volts. For 7.5 volts, the input goes down to just below 21 volts. These are of course voltages with no load applied. It will be somewhat less when loaded. The manual says that the power supply runs at a slightly higher voltages internally to make sure it can reach the stated maximum output voltage in all cases. If you press just one of the switches at a time, you get exactly what the range is set to be. So 30 volts, 1 amp, 15 volts, 2 amps, and so on. But what I really like is how the designer managed to get a lot more by allowing the switches to be pressed together. Say you started with a 30 volt 1 amp range. If you now press the button for the 15 volts 2 amp range in addition, the output changes to 0 to 15 volts, but the current limit stays as 1 amp instead of 2. If you now hit the 7.5 volts 4 amp button, the output drops to 0 to 7.5 volts and the current limit stays at 1 amp instead of 4. You can actually release the 15 volts button and nothing will change. The principle is that if 2 or more buttons are pressed simultaneously, the voltage is the one of the lowest range and the current limit that of the lowest current, which is what this table here shows. Of course, these days we are all used to variable current limits in the milliamp granularity, and yes, 1 amp as the lowest limit is still a lot of current, but with that neat trick, the power supply is a lot more versatile than you would assume. Versatile it is, but service-friendly it certainly isn't. There's also no disassembly instructions in the manual. Well, to get better access to the main PCB, that voltage selector has to go because it holds the PCB in the rear panel. This is an interesting way of selecting voltages using PCB connections with a rubber bung bridging some traces. Sadly, it also puts mains voltage on at least parts of the PCB, which makes works on this, let's say, exciting. The other side of the PCB is locked by the buttons, so the front panel has to be loosened enough to get them out. There are also 4 comparatively easy to remove screws in each PCB corner that I did not show. But now the PCB is essentially free, but it hardly moves. That's because of all those very stiff cables, some of which are soldered in. And check out that white wire going straight across, soldered in on both sides. You have to dismantle at least to that stage to have a chance to access the fuse. Who came up with this arrangement, I wonder? Well, after desoldering the white wire, removing some more screws and some gentle bending of stiff wires, this is the maximum disassemble I dare to do. Anything more would require a lot of desoldering of wires. That in itself isn't a problem, but I need this thing to work to troubleshoot the problems. In the end, I even soldered the white wire back to be able to do some tests. But first, while it's in this state, I might as well replace the electrolytic capacitors like these 3 on the little PCB on the front panel. And done. It's actually not easy to find axial electrolytic capacitors these days. Not much choice, but I hope these will last a while. Note how much smaller they are, also they are exactly the same capacitance and voltage rating as the old. The PCB had holes for smaller size caps which are made use of. Replacing the 2 electrolytic caps on the main PCB is much harder because of all the wires preventing good access. There is a black cap of 470 microfarad 40 volts for the separate power supply driving the regulating electronics, and there is the enormous 4700 microfarad 63 volts cap for the output voltage. Both of these caps are secured with tie wraps. I managed to desolder and get them out, and here's a comparison of the old and new main capacitor. Maybe the 8003 on the cap is a date code, like March 1980. That seems about right. All the new caps are in place. I even managed to put tie wraps around them. There is a trim pot to adjust the max voltage in the 7.5 volt range, which sets it also for all the other ranges, but it's impossible to adjust it down to 7.5 volts. The lowest is about 12 volts, so it's definitely something broken. A closer look again at the schematics, but without going into the complexity on how this all works. It is all in the downloadable service manual if you are interested. For now, just this. RV2 is the trim pot to adjust the max voltage. The 30 volts, 15 volts and 7.5 volt range are all determined by these resistors and the switches. The selected range resistor combination provides a reference current together with diode MR7 and the voltage adjustment potentiometer RV6 on the front panel. If the 5 volt switch S6B is not engaged, this goes to the base of transistor VT1 to tell the rest of the regulator circuit the desired output voltage. If the 5 volt range is selected, the switch S6B selects a simplified copy of that circuit consisting of the trim pot RV3, the diode MR6 and resistor R4 instead. It is really the same thing, except that there's just one range, namely 5 volts, and the adjustment is done with a trim pot instead of the front panel knob. Since the 5 volt range works, everything from the base of transistor VT1 onwards is working as it should, and since the 30 volts, 15 volts and 7.5 volts range switching kind of works and adjustment with RV6 is possible, it is unlikely that any of these are faulty. This leaves diode MR7 as the prime suspect. Access from the component side is very tricky, as you have seen, but easy from the solder side, provided one knows where things are. Sadly, the service manual does not include a diagram of the PCB. I made my own by shining a lamp on the component side and taking a picture from the solder side. Then I used the schematic to overlay some components. Of interest here are the diodes MR6 for the 5 volt range, which works, and the diode MR7 for the other ranges. While using the meter in diode mode, of course the power has to be off. And because this PCB has sections on mains voltage, the unit must be unplugged as well. I tested MR6 first and that worked as it should. Now to MR7. Nothing. That should have shown the forward voltage of around 0.5 to 0.6 volts, but just to check the reverse polarity, also nothing. This diode has failed open. According to the service manual, this diode is a simple 1N4148, of which I have plenty. To confirm the diagnose, I soldered a new diode temporarily in parallel to the failed one. It looks a bit different because I used convenient spots of the PCB, but they are directly connected to the MR7. With a temp diode in place, the 7.5 volt range now reads too low, because I previously adjusted RV2 to the lowest setting. But with some patience, it's now possible to adjust RV2 so the max voltage in the 7.5 volt range is actually 7.5 volts. And furthermore, it can now be adjusted all the way down using the front knob. The max voltage on the 15 volt range is about right, and the same for the 30 volt range. With some difficulties, I managed to desolder the dead MR7 and put my temporary replacement in its place. I don't know why the original diode failed. It isn't stressed in this circuit, but just in case I mounted it a bit away from the PCB for better air circulation. A quick verification of the amp meter. 5 volt range and 1 amp load. It shows 1 in a 6 amp range as you would expect, and 1 in a 2 amp range. Increasing the current to 2 amps, and it now shows full scale in the 2 amp range and 2 in the 6 amp range. Going all the way to 4 amps and the meter is maybe a tad below 4, but I can live with that. Of course, trying to exceed 4 amps triggers the current limiter, collapsing the voltage. Loading the 30 volt range with 1 amp, no problem. And the current limiter works when I exceed 1 amp and recovers when I reduce the current back to 1 amp. If I press the 15 volt button in addition to the 30 volt range, the max voltage reduces to 15 volts. In this mode I can throw 1 amp at 15 volts, no problem, but as soon as I exceed 1 amp, the current limiter is triggered, even though normally the 15 volt range can handle 2 amps. This is as discussed earlier, the power supply always uses the lowest voltage and lowest current limit when more than one button is pressed. To verify some of the specs, here's the warm-up behavior. This is the 5 volt range. The blue trace is the output voltage, the red trace the inside temperature, and the yellow trace the outside temperature in degrees Celsius. After turning on and no load, the power supply takes about 1 hour to reach a stable voltage, but while that climb looks dramatic, it's just 7 millivolts in total, so really nothing. Over the next hour, the inside temperature increases by 3 degrees, but the output remains stable. I then applied a 1 amp load, which causes a drop by 14 millivolts. The output takes a while to stabilize, but it stays within 2 millivolts, while the temperature climbs to 38 degrees. I'm quite happy with that performance. And here the load curves for 5 volts, 15 volts and 30 volts. I did not do 7.5 volts because that's essentially the same as the 5 volt range. The 40 millivolt drop at 4 amps is more than in the spec, but measurements at these currents are quite difficult. 40 millivolts at 4 amps is 0.01 ohm and well into the range caused by contact resistance of the measurement leads in the sockets of the power supply. To measure this more exactly, I would need to make myself special test leads, but I decided not to bother. This drop is actually what you get if you use normal banana plugs, so much closer to actual use. The noise and ripple is with less than 0.1 millivolt at 10 volts 1 amp load quite acceptable. For comparison, this is the noise and ripple of a bench switch mode power supply at the same setting. This video is getting already too long, so very briefly, this is a D model, which means it has a split output. This is a schematic for that part. As you can see, it's quite an elaborate setup. VT20 and VT21 are additional power transistors on the heatsink. Basically, the job of this circuit is to keep a virtual center tap floating in the middle between the two normal output terminals. The spec says it keeps the center tap at 49 to 51% of the total output down to 4 volts. It works quite well even at lower than 4 volt settings, right down to when the total voltage goes below 1.4 volts or 0.7 for each leg. But in practice it would be rare to use symmetric voltages that low. Here's a more realistic scenario with 24 volts total output and the 2 meters are showing the split part of 12 volts each. If I add a 10 ohm load resistor only on the lower leg, the current limiter is triggered and the voltage of both legs is reduced to maintain symmetry. The same happens if I add the load only to the upper leg. Regardless on how the load is distributed or the current limiter is triggered, it tries to maintain the symmetry. Not bad. And that's my repair of the WEIR 413D. If you like my videos, don't forget to subscribe. There are more repairs and reviews coming up. And it would be great if you decided becoming a Patreon. That would really help this channel. As Patreon, you always get early access to videos, a blog and other exclusive content. Thanks for watching.